Hi everyone, and welcome to my presentation of my course project entitled An Exploration of Fuzzy C-Means Clustering. So just an overview of what I will cover in this presentation. I'm first going to provide an introduction on the experiment and the fuzzy logic and fuzzy C-means clustering that are at the center of it. Then I'll provide a little bit of background on the development of these theories. And then from here, I will go into detail on the fuzzy C-means algorithm and how it compares to the more traditional K-means clustering algorithm. And then from there, I will give more details about my experimental design and methodology, and finally share with you my result with a brief discussion of areas for improvement or future exploration at the end. Okay, so just as an introduction, fuzzy logic is a form of reasoning under uncertainty that is intended to model situations with vague or otherwise imprecise parameters. So the premise is basically to assign degrees of truth to propositions beyond the realm of the classic true-false binary divide. That is to allow for degrees of truth or partial truths. And fuzzy C-means clustering, which will be at the center of this experiment, is a soft clustering algorithm which assigns probabilities of belonging instead of absolute belonging, like more traditional clustering algorithms. And the purpose of this paper will be to conduct an experiment comparing the performance of fuzzy C-means clustering and traditional K-means clustering algorithms on a series of classification tasks. So just to provide some background, probability theory was a school of thought that dominated thinking about uncertainty for a very long time. So the basic concepts of probability theory emerged as early as the 1500s and were more formally developed as time went on by mathematicians like Bernoulli, Bayes, and Laplace. And probability theory continued to guide thinking about uncertainty until the mid-20th century. In 1937, Max Black developed this concept of vagueness, which he defined as a proposition where the possible states of the proposition are not clearly defined with regard to inclusion. In 1965, Lofty-Zadeh took this a step further by creating the distinction of fuzziness within the realm of vagueness. And today, fuzzy systems are thought of as universal function approximators, and they have a variety of applications in a variety of fields. For this experiment, we're going to look at classification, which I'm sure most of you are familiar with, but just as a refresher, classification is the task of determining which of a set of classes or clusters an observation belongs to. So K-means clustering, a pretty traditional clustering algorithm, partitions the dataset into groups of clusters, assigning absolute membership to a single cluster for each point. So this is a hard clustering algorithm. And fuzzy C-means clustering also partitions a dataset into groups of clusters, but allows for the possibility of belonging to more than one cluster by assigning probabilities of belonging rather than absolute membership. So this is a soft clustering algorithm. Just to go over the mathematical framework for each. So for K-means clustering, the first step is to determine the number of clusters and randomly select initial centers. From here, the algorithm for each data point determines the shortest distance to the cluster center, assigns membership for that point to the cluster with the closest center. From there, the algorithm recalculates the cluster centers once all points have been assigned and calculates the value of the squared error. And then finally, these steps are repeated with the clusters being redefined and centers being moved until the squared error falls below a defined threshold or a predetermined number of iterations have been completed. Fuzzy C-means clustering is pretty similar conceptually. It has a few important differences. So the first step is the same, which is to determine the number of clusters and randomly select initial centers. But the second step is a little different. So for each data point, the algorithm calculates fuzzy membership, which is a probability of belonging to different clusters, rather than the absolute membership we saw in the previous algorithm. And from there, the algorithm recalculates cluster centers and the value of the objective function. And then once again, these steps are repeated and the clusters are reorganized until the minimum J value is achieved, where J is the objective function, or the change in the partition matrix falls below a predetermined threshold. Okay, so to go a little bit further into my experiment, my goal was to compare the performance of the fuzzy C-means and traditional K-means clustering algorithms on 8 separate classification tasks. And I measured performance by accuracy of classification, meaning that the algorithm correctly predicted which class or cluster each point would belong to. And my hypothesis was that performance would be similar for the two algorithms on tasks where the clusters had distinct boundaries, but the fuzzy C-means would outperform K-means on tasks where the clusters had overlapping or less distinct fuzzy boundaries. Just to get into my methodology, so as I mentioned, I completed 8 total experiments, varying the number of clusters within the sample data and whether the clusters had distinct or overlapping boundaries. I experimented with data sets having 3, 4, 5, or 6 clusters, and each cluster contained 200 data points randomly generated by Python after I specified cluster centers and sigmas, which is the spread or dimensions of the cluster. So we have pictured here, we have 2 sample data sets, both of which have 4 classes or clusters, but we can see the one on the left has fuzzy or overlapping boundaries, whereas the one on the right has distinct boundaries. The clusters are more cleanly separated from each other. So once I had the data built, I ran both the fuzzy C-means and traditional K-means algorithms on the raw XY coordinates for each data set with the goal of accurately predicting which cluster or class a given point belonged to. So thinking about this visually, if we go back to the previous slide, we have the raw data divided by class here on the left side for the overlapping case with 4 clusters. And then what the algorithms do is try to recreate basically this map as accurately as possible and assign the points to the correct clusters. So we can see here, just looking at it by color, the 2 maps created by fuzzy C-means and traditional K-means are very similar. We do see a couple of points that have different colors, meaning they were assigned differently. But overall, things look pretty good. So just to formalize my results, I have a little table here which has overall accuracy rates by method, meaning K-means versus C-means, divided out by number of clusters in the data set and whether the clusters were distinct or overlapping. So I'll just leave that on the screen for a moment to give you a chance to look over it. Okay, and next I have just a graphical representation of these results, which I think is a little bit easier to compare visually. So we have on the left here a figure which has accuracy rates for the classification task with overlapping classes, and then on the right here, accuracy rates for the task with distinct classes. And I'll just give you a moment to review that as well. Okay, so now just to sort of put into words the results that we were seeing in the previous tables and figures, as you can see, both methods performed quite well overall, with accuracy rates exceeding 90% for all tasks. There was especially strong performance by both algorithms on classification tasks with distinct clusters, with a 97% accuracy rate or higher for both methods. Again, these were thought of as the slightly easier classification tasks because the classes were more distinct and did not overlap at all. As expected, we did see that for 3 out of the 4 tasks, fuzzy C-means outperformed K-means when the clusters were overlapping. So just here, to go back to the previous slide, we have the accuracy rates for overlapping class tasks, and we have C-means outperforming K-means for cases with 4, 5, and 6 classes in the data. And then finally, sort of an interesting trend was that the fuzzy C-means algorithm slightly outperformed K-means on all data sets with 4 or more classes, overlapping or distinct. But overall, performance for both methods deteriorated slightly as the number of classes within the data set increased, which I think is something that is pretty commonly seen with classification tasks. Okay, and just to wrap everything up, so while the experiment did yield some interesting results, I believe there are some areas for improvement or future exploration, things to dig into further. So firstly, I think it would be interesting to evaluate performance on clusters of heterogeneous size instead of uniform 200 points per cluster. That would potentially, again, make it a little bit more difficult if the clusters were not all like each other, at least in terms of size. It would also be interesting to use real data sets found in nature instead of Python generated random data points. I would also like to experiment with data sets of varying sizes. For example, how do the methods perform on small data sets only like 100 data points, or how do they perform on large data sets with tens of thousands of data points? And then finally, I think it would be interesting to continue to increase the number of clusters in the data to see if the trend of fuzzy C-means outperforming K-means would persist. So thank you for watching my presentation, and I look forward to hearing your feedback.